So in this next lesson we're going to talk about alkenes, and alkenes was something that we discovered at the end of the last lesson, and alkenes are a homologous series. An homologous series are a group of molecules that differ by the number of carbon atoms they have in their chains, and they share a functional group. They all have the same functional group. So that might be alcohol, it might be carboxylic acid, or in this case, it's a double bond. So in this case, a double bond for alkenes. And you need to be careful because alkenes have an E, and they're very, very similar in name to alkanes, which have an A here. So don't get them confused. Alkenes have the double bond, and alkanes have a single bond. And it's a carbon-carbon bond, so I'll draw those in. So carbon-carbon single bonds on the alkanes, carbon-carbon double bonds on the alkenes. So let's look first of all at the structure of alkenes. So alkenes are sometimes called unsaturated. So if you've heard of saturated and unsaturated fats, this is the same word. And unsaturated means that it doesn't have all of the hydrogens that it could have. So if I show you quickly a fat molecule, so don't worry about this end for now. So these long chains of carbons that I'm drawing now, these skeletal formula chains, these are the fatty bits. This is what makes it kind of greasy. And these chains, you can see, have got all of the hydrogens on them. So if I was to draw all of the hydrogens in, it would take a long time, it would get very boring, but I could draw all the hydrogens in on these carbons. Remember, for skeletal formula, we don't draw the hydrogens, but they are there as much as they need to be there. So I could draw all of these hydrogens in and so on and so forth. And that means that they are saturated, so that there is many hydrogens as there can be, which means that there are no double bonds. Let me explain. If there was a double bond here, that would mean that there was only now one hydrogen here and one hydrogen here. Whereas if that double bond isn't there, there are two hydrogens here and two hydrogens here. So there are more hydrogens. So this is saturated, whereas if I add the double bond here, then I've reduced the number of hydrogens. And every time I add a double bond, I reduce the number of hydrogens further. Okay, so I'll draw the hydrogens in now. And if you remember, carbon has 4 bonds around it typically, so if I look at this centre that I'm drawing in green here, that centre currently has 4 bonds, 2 from the double bond, 1 from to the other carbon and 1 to the hydrogen. And if I look at this centre down here that I've now circled, this has got 2 bonds to carbon, and it's got then 2 bonds to hydrogens. Okay, so to maintain its 4 bonds around its centre, 4 covalent bonds, unsaturated carbon chains have double bonds in them, and that reduces the number of hydrogens that are bonded. And saturated carbon chains, such as this one at the top, have as the maximum number of hydrogens that it's possible for that chain to have. So this top chain is saturated, and this bottom chain is unsaturated. So if we just dive in now and look at the structure of a double bond. So I'm going to pick this double bond here, and I'm going to just draw that out nice and big for us down here. So I've got my carbon, and I'm going to draw it non-skeletally for a moment. Got my carbon here, goes off to another carbon there, goes off to another carbon there, and then I've got, and I'll draw these in a different colour, got my hydrogen down here, and I've got my hydrogen down here. So this is my enlarged version of this carbon-carbon double bond up here. And if we now just again look deeper at this part, this carbon-carbon bond, so I'm going to take this over here. I've got one carbon, I've got a single bond that goes between them like this, and we've talked about this before, that the single bond, the electrons in the single bond look a little bit like this. So kind of just a blob in between the 2 carbons. And there are 2 electrons in here, so I'll draw those as red. There's one from the carbon on the left and one from the carbon on the right, because this is a covalent bond. And then the second bond sits above and below the carbon pair like the bun in a hamburger. So this maybe looks like it's two bonds, but that's just one bond, that orange pair. And again here, I've got one electron from the carbon on the left and one electron from the carbon on the right, and they sit in those clouds and hold the carbons in place so that they can't rotate. If you remember, we discussed in a previous lesson, the carbons can't rotate if there's a double bond, because this pair of electron orbitals, we call them, prevent that from twisting. Now what this means is that there is an area on a carbon-carbon double bond of high electron density. High electron density. Compared to a carbon-carbon single bond. So that means that a carbon-carbon double bond is, and if you think about it in terms of electrophiles and nucleophiles, remember electrophile is something that likes to receive electrons, and a nucleophile is something that has a source of electrons. And so because we have our area of high electron density here, this can act as a nucleophile. Now, it's not the world's strongest nucleophile, but if you pair it with a strong electrophile, so carbon-carbon plus, and if I draw the electrophile as E plus, then you can get this reaction mechanism where the carbon-carbon double bond comes and is drawn to the electrophile. It's drawn to this lack of electron density on the electrophile from the high electron density on the carbon-carbon double bond. And this can then lead you to form a new compound which has got the electrophile bonded to one of the carbon atoms and the positive charge left on there. So we're going to look at that in more detail now. So just remember from this that carbon-carbon double bonds are areas of high electron density, and this allows them to act as effective nucleophiles in mechanisms and reactions. So let's have a look at some of those reactions. So these are all addition reactions. What that means is we take an alkene and we add something to it. That's called an addition reaction. So we add something to it, which I'm going to call AX, and then I'm left with a single molecule, which will be CACX, and then whatever I had on here before is still there. So let's have a look. So there are three different addition reactions you need to know. I'm going to use RXN for reactions shorthand. And these are with hydrogen bromide, with sulfuric acid, and with bromine. And we're going to look at these one at a time, but they're very similar. The first two certainly are very similar in terms of the reaction mechanisms. So let's look at HBr. So if we start with a carbon-carbon double bond, and let's just pretend we've got ethene here. So I've got all carbons. And I've then got hydrogen bromide. Now, if you remember, hydrogen bromide, because bromine is going to have an electronegative difference to the hydrogen, there'll be a bond polarity in this molecule, and that means one end will be a little bit positive, one will be a little bit negative. And this double bond on the carbon-carbon, on the double bond of the carbon-carbon, can reach out and touch fame, can reach out, and it can grab this hydrogen, because this hydrogen is going to be a little bit positive. And when it does that, the electrons can go from the bond here into the bromine, because the bromine is more electronegative, it's pulling them in. And when that happens, we're left with a broken carbon-carbon bond. So this carbon-carbon bond in red has been broken. So that means I'm left with a single bond now, because I've broken the double bond. I've got my hydrogen here from the HBr. I've got the other hydrogens that I already had. But this carbon on the left, this carbon here, has now got a positive charge on it. It's got a positive charge on it because the electrons in the bond that have been broken have left and have gone to form a new bond. So this new bond has been formed, and that means that the electrons that this carbon we're expecting to see around are no longer there. So that carbon now is positive because it's lacking some electrons which are negatively charged. So then what happens is, well, I've now got Br minus floating around as well, because the electrons in the bromine over here have ended up just on the bromine, not in the bond. So now that's negatively charged because it's got a higher than expected electron density, and that means I've now got a positive charge and a negative charge. So you can see what's maybe going to happen here is this negative charge on the bromine is immediately going to go, and I'll get a flow of electrons shown by a curly arrow to the carbon. So this then means that we end up with the single reaction product, which is carbon-carbon single bond now. On the right hand side I've got two hydrogens that were from the original reaction and one hydrogen from the HBr, and on the left hand side I've got two hydrogens in the original reaction and one hydrogen from, one bromine from the HBr. So I'm left with this, which is bromoethane. So this is the reaction mechanism to convert from ethene and hydrogen bromide to bromoethane. That's all very well. What about one of the other examples? What about sulfuric acid? So this is a simplified version of sulfuric acid, which, as you know, is H2SO4. Sorry, this should be the 3. And I've got my molecule up here. Now I'm going to make it a little bit more complicated this time. I'm going to add some more functionality to this. So I'm going to make it part of a longer chain. But it's exactly the same mechanism, and I'm drawing it in skeletal formula as well to show you, but it's the same mechanism. So I start from my double bond, and I come and I grab this hydrogen, because this hydrogen it likes to be a little bit positive, because the sulfuric acid is pulling electrons in like this. So I then got and then exactly the same thing happens, that this negative charge now loves to go for this positive charge, and I'm left with this product. Now, you might be thinking it would have been perfectly reasonable when I did this step to, instead of ending up with the hydrogen here, to instead put the hydrogen here. So let's do that as well. Let's go this way for this step. So in that case, I'd end up with this molecule, and then I would react again with the remaining negatively charged OSO3H. And so if I now show you both of these reaction products, I've got one here and I've got one here. Now these are very different, because on the one on the right the functional group sits on the middle carbon atom, and on the one on the left it sits on one carbon in from the end. So I'll just redraw these for you so you can see that difference nice and easily. So I've got essentially this chain in both cases. I've got a 5 carbon chain, and up here I've got a 1, 2, 3, 4, 5 carbon chain. But on the one on the left, my functional group sits here, and on the one on the right, my functional group sits here. And how do you go about working out which of those two products is formed? Because mechanistically, we can draw either of them. And you'll be pleased to learn that there's a set of rules for working this out, but also you can explain it, so you don't need to remember the rules. And if we look at it in this context, I can explain why. If I have a double bond like this, and on this side I have another carbon atom with some hydrogens, I have a methyl group. When this double bond is deciding whether it should go to this side or to this side, when it's forming its positive charge, or rather, to put it a better way, whether the electrons will flow away from this side or will flow away from this side, you can look at the positively charged molecule which is formed in the intermediate step. So if I take the electrons here, and let's say I've got my H plus here. If I take the electrons from this bond and I go this way and I form, oops, sorry, I form this with the positive charge here, or I could go the other way and I would form the positive charge here. The question is, which of those two is more stable? So we'll just join the other one. So I've got two routes. I could either go the red way or I could go the blue way. In fact, let me make that blue for simplicity. So this is blue. So if I go the blue way, I end up with the positive charge at the blue position. If I go the red way, I end up with the positive charge at the red position. Now, the positive charge on the red position is less stable than with the positive charge on the blue position. And that's because having adjacent carbon atoms, like this one, they push electrons into the structure, into the molecule. So that has the effect of making this positive charge less positive. So instead of being like 1 plus, you can think of it as being more like sort of 0.9 plus. So it's not a full positive charge because this methyl group donates some of its electrons into that positive charge, and that stabilizes it, makes it less positive. Things don't like to be charged. When they're charged, they're unstable. Whereas in the red position, there is no carbon atom to do that donating. The only one that's available is the one on this side from this direction, and that's exactly the same on the blue side. You could donate either way along this bond, so here. So on the blue positive charge, I have 2 carbons donating, and on the red positive charge, I only have 1. So that means that the route with the turquoise arrow is more likely to happen because the intermediate carbocation, or positively charged carbon molecule, is more stable. So in this case, you would end up with much more of the material with your hydrogen at this end. So if this was HBr, you'd end up with much more of this compound than of this compound, because of the stability of the intermediate carbocation, and that stability comes about by the number of donative groups. We call these donative groups, or they're donors, electron donors. So this is electron donating, which stabilize the positive charge by reducing it effectively. And this is true for any group, so it doesn't just have to be a methyl group. So if another group is also donating electrons, then that will stabilize the positive charge as well. But typically you'll just have to deal with which end has the more carbon groups on it. So if you're presented with a molecule that looks like perhaps this, which is often what happens, this is straightforward because the carbocation in the position I'm drawing in green will be much more stable than the carbocation in the position in yellow because of the donation of the groups. So let's summarize all of this by showing you a series of different alkenes, and in each case we're going to react it with HBr, and in each case you get 2 products. You get a major product and you get a minor product, and the major product is where you have the more stable carbocation in the intermediate. So for this first one, which is ethene, it's evenly distributed between the left-hand side and the right-hand side, and actually anyway these molecules are completely equivalent. For this one, which is propene, we put these names in here. This is ethene, this is propene, and this one is 2-methyl propene. So for propene, you could have 2 reaction products here. You could have this one, or you could have, you could have this one, or you could have this one. And the one on the left would result in the carbocation being in the position here, and the one on the right would result in the carbocation being in the position here. So the one on the left is the major product. So you form more of this product, and the one on the right is the minor product. So you still form a little bit, but you form far less because there is a far less stable carbocation in the intermediate. On the right, the products are, as you'd expect here, bromine here, and bromine here. And again, the one on the left is the major product because the carbocation is more stable, and the one on the left is the minor product. So I'm going to go through this a little bit more because it's a slightly confusing concept sometimes. So let's just look at, if we start with this double bond and we add HBr, then I'm left with a carbocation because I've added the proton, the hydrogen. So I've got my hydrogen at one end of the bond and I've got my positive charge at the other. And so using this model, we're going to look at these three different possible scenarios for primary, secondary and tertiary intermediates. And by that I mean, if in the position where I've drawn the red circle, if there were no carbons there as I've drawn, then you get primary carbocation. So that's where you had just carbon, two hydrogens, carbon, and then there's a positive charge in it. This is a primary carbocation. Or in the red position over here, if in that red position I had one additional carbon bond, then I would have a secondary carbocation, so that would look like this. And if in that red position I had two double bonds bonded to the carbon, then I would have a tertiary carbocation. And remember that the more carbons you have surrounding the positive charge, the more it's stable. So that means that the rate of reaction goes like this. So tertiary progresses more rapidly than secondary, which progresses more rapidly than primary, because this carbocation is more stable. So because this carbocation is more stable, you get more of a product where the carbocation is on this carbon atom than on the other carbon atom, because the one on the left here is primary and the one on the right is tertiary. And carbocations prefer to be tertiary than primary, prefer to be tertiary than secondary, and secondary carbocations are preferred over primary carbocations. So this means that in the examples we have above, which I go back to now, the example on the left forms a primary carbocation, the example on the left can form a secondary carbocation, and the example on the right, the example in the middle can form a secondary carbocation, but the example on the right can form a tertiary carbocation. And that determines the major and the minor products. So if we have one more example here, if I have this molecule, and I react this with HBr, I could go one of two ways again. And I could have a carbocation, and I'm going to use two different colours here. So I could either go this way, or I could go this way. Let me put an HBr here as well. Complete this mechanism. So, in fact, actually, let me change colours for one of these and make it a little less confusing. So let's have green here. So I could either go on the green direction, or the green direction, or I could go in the turquoise direction. And if I go in the turquoise direction, which I'll use this arrow for here, then you're left with the carbocation looking like this. And if I go the green direction, which is this direction, I'm left with the carbocation that looks like this. And so you can see that in the top example, with the red circle now, this is a tertiary carbocation, tertiary. And in the bottom example, this is a secondary carbocation. So remember, tertiary and secondary just relate to the number of carbon atoms that are bonded to the charged carbon. And we know that tertiary is preferred over secondary, and therefore we know that the top one will be the major product, and the bottom one will be the minor product. And so if I complete these, I'll end up with two products. Oops. And of these two products, we know that number one will be the major product, and number two will be the secondary product, the minor product. And this is sometimes referred to as Markovnikov's rules, or Markovnikov rule, and this is a rule that allows you to explain where the electrophilic part of the added molecule will go and where the hydrogen will go. And so this mechanism works equally well for hydrogen bromide or for sulfuric acid. There is a little bit of a change, however, when we look at bromine, and that's because bromine obviously contains two atoms that are the same. So here there's no ambiguity as to which one will go where. So if I have this, if I add bromine to this, the two reaction products are the same because the bromine will add at either side, like that. So in bromine's case, there's no possibility to have a major product and a minor product. Bromine just adds across the bond. And the mechanism for that we'll look at now. So if I add my bromine here, what happens is this bromine actually rotates so that it's like this. And it approaches the double bond like this, end on. And this double bond then comes and grabs one of the bromines, kicks out the other one. And again, as I say, you can add to either end here, but it'll add to the end that gives the more favoured carbocation, like that. And then we've got Br minus left over from the first step, and so this Br minus can now jump in and it can flow its electrons to that carbocation centre to finish off the molecule, so that we end up with, as above, this. So it's a simple mechanism where you just attack the bromine and create a negative bromine and a positive bromine by splitting it up. Like this. So those are the three that you need to know. So we need to know those three mechanisms. So for any alkene, you need to be able to add HBr, and you need to be able to explain the major and the minor products. So we end up with two here. We end up with this one and this one. And the easy way to remember is that the bromine always adds to the more substituted end, the end with the more carbons on it. So this will be major, and this will be minor. Let me do that in a different colour. This will be minor, this will be major. And then again, same thing with sulfuric acid, H2SO4. Again, you'd end up with two products here, OSO3H, and this would be, and then this would be minor, minor, and same thing again here. So OSO3H, and this would be the major product. And then finally, you need to be able to do the addition with bromine, and this gives you, oops, this gives you simply bromine added to each end. And there's only one product here because the addition product is the same for both of the sites. So there's one final thing to mention, and that is that if you notice that bromine here is used up in the addition of bromine to a double bond, and that means you can use bromine in water to test for double bonds. So bromine water is a test for the presence of double bonds, and it decolors the bromine water as the bromine is used up in the addition to the double bonds. And so that's a practical you might do, or you might have done, but you might not have done it. But it might come up as an exam question, and so you just need to be aware that bromine water can be used to test organic compounds for what we call unsaturation. So the key takeaways here are major and minor products in addition reactions when the alkene is asymmetrical or unsymmetrical. You need to understand why that's the case, and that's that addition using the carbocation stability argument. You need to be able to do the mechanisms for those reactions, and then go on to talk about relative stabilities of those carbocations in relation to the number of carbon groups that surround them, and the fact that those carbon groups are donating their electron density into the carbocation. And next we're going to look at addition polymers, which opens up a whole new world of organic chemistry. So let's look at that in the next lesson.